started. So welcome to our Q&A and live lecture overview session for last week's videos. What have we talked about last week? Well, lectures 7 and 8 were concerned with two different topics. So in lecture 7, we discussed more details about concurrency and especially problems with deadlocks and starvation of processes. So we looked at how do we define a deadlock, what are the necessary and additional conditions for a deadlock to occur, how can we model this inside of an operating system using resource allocation graphs. And then we looked at a classical problem, Dijkstra's dying philosopher's problem, which is, obviously just a nice example of things that would never happen in the real world. And then we talked about how to prevent deadlocks, how to detect and possibly resolve them. And lecture 8 was concerned with completely different things. So there we went very much hands-on and we dug a bit deeper into how programs are built and how programs are executed. So we looked at the way from our source code to a running process in Unix. So first we had a look at compilation, like pre-processing, compiling, assembling, linking, and so on. We took a look at, well, in which formats executable files are represented. So ELF for Unix, which is the most common executable format for Unix nowadays. We looked at what a linker did, how symbols behave and what symbols are used for. And then we had an introduction to virtual memory and looked at process memory layouts in Unix. And finally, took a look at how fork and exec system calls interact and how they work together with a program startup. So let's jump right in. We've seen this nice example of a crossroad where there is a yielding situation that left yields to right. So whenever, as you know, when a car there's no traffic lights or anything indicating that somebody has to yield. So in the default situation, if a car comes from the right, and you're not in the UK, so if a car comes from the right, you have to yield so that other car can come first. And if we have the situation shown on the top right part of the page here, then obviously we have a deadlock because every of these cars has a car to its right. So there is no obvious solution if we only follow that rule. Obviously, in traffic rules, there is a way to resolve situations like this. So Stallings in his textbook defines a deadlock as a situation in which two or more processes are unable to proceed because each is waiting for one of the others to do something. And we've seen different things that can happen when we have such a situation where we have mutual waiting for things. So the first one is a deadlock. So we have passive waiting in blocked process states, but we can also have live locks. So we can have active waiting. And live lock means that processes can be in an arbitrary state, including running, but none of the involved processes is actually able to proceed because one is waiting for the other to proceed, and the other one is in turn waiting for the first one to proceed. Now, deadlocks actually are the lesser evil because this is a state we can discover because processes cannot proceed, whereas in a live lock, our process still continues executing instructions, but it just can't really make any useful progress here. So for deadlocks, we have a basis to resolve it, and we'll take a look at if this actually works out later on. Active waiting, as in live locks, results in an extremely high system load. So you'll probably notice this when your fans in your laptop turn on because you have an active waiting deadlock situation. So we took a look at more formal definitions, like what conditions actually have to be present in order for a deadlock to occur. So we first looked at the first 3 conditions here. So we need exclusive allocation of resources. So either process 1 or process 2 can have a resource, but not both at the same time. And of course, no process may access a resource unit that has been allocated to another process. Remember, this requires discipline. If you just ignore all synchronization operations and access a resource, you can do it because there's no hardware preventing you from doing it usually. But of course, you'll mess up your program results. The second thing, the second condition that has to occur for deadlocks is the allocation of additional resources. So whenever we have one resource and we have allocated it, we are trying to allocate another one subsequently. So hold and wait. So this means we're not allocating all the resources we need at the same time, but we're doing it in steps. And in between these steps, a process switch or thread switch to another process or thread can take place. And this other process or thread can then try also to execute allocations for single resources. And condition number 3 is that there is no removing of resources, so no preemption. So that means that the operating system is not allowed, if we successfully hold a resource as a process or thread, then the operating system is not allowed to take it away from us because we wouldn't expect it. So the expectation of the programmer is as soon as I have allocated a resource, then I can use it until I release it. And if I would take away as an operating system this resource in the middle of executing a program, then that might have some strange consequences. Now, these are necessary conditions for a deadlock to occur, but only if a fourth condition, an additional condition, occurs at runtime, then this really leads to a deadlock. And this is this circular waiting, which is in the first place a bit difficult to understand maybe. So a circular waiting means we have a chain of processes where one process waits for something of the other process to release and vice versa. So essentially, this gives us the situation that none of the processes can continue until the other one releases something. And since both are blocked, both are unable to release the resource the other one is waiting for. And we've also seen how to model these relations here. So we've seen resource allocation graphs. So these are used to visualize and then also automatically detect deadlock situations. So a resource allocation graph describes the current system state, and we have two types of nodes in this graph. One type of node are processes, and the other one are resources. So we have edges in this graph, and these edges show either an allocation or a request. So an allocation is an ingoing edge to a process, whereas a request is an outgoing edge from a process. So in our example here, we have, for example, process D, and this holds resource S, and it requests resource T to the right. And we have this circular waiting condition if we can find a circle in this graph. So a circle, of course, meaning that all arrows in this circle have to go in the same direction. So the one indicated in red here, so D holds T, but D requests T, excuse me, but T is already held by E. E requests V, V is already held by G, and then we have the thing closing the circle, G requests U, but U is already held by D. So this circle means that we can't break it because each of the processes D, E, and G is waiting for something to occur for release, and that won't happen. So there's a question, is B also deadlocked in this situation? If you look at the new theoretical exercise, I'm not going to answer this here, but you can think about this. Sorry, that would give you an answer to one of the questions of the current theoretical exercise. But yes, it's a good question. So these resource allocation graphs look like a very useful tool for detecting deadlocks, right? Well, the problem is that in a real computer system, these graphs tend to be very large. So you can have like hundreds or thousands of resources. Like consider you have each memory page as a resource, for example, and you have 4 gigabytes of memory distributed in 4 kilobyte pages. And well, you have 1 million different resources for memory pages alone. So this graph has to be updated for each resource allocation and deallocation. And then you would have to look for a circle in this graph after each update. And looking for circles in graphs is a relatively complex operation. If you're interested, you can probably look up in one of Dijkstra's papers how to do this. I'm not going into details here, but that should be covered by some theoretical computer science course, I guess. Nevertheless, it's expensive. That's what you need to know here. So then we took a look at one very old problem, which is the dining philosopher's problem. And yes, this is a bit artificial. So we assume we have a set of philosophers, so 5 philosophers here, and philosophers do one of two things. So they're either thinking or they're hungry, and when they're hungry, they want to eat spaghetti. And in order to eat spaghetti and not to soil your clothes, you need 2 forks. Now the problem is that there's enough spaghetti, but there's only 5 forks for 5 philosophers. So essentially, well, it's obvious that not all 5 philosophers can eat at the same time. And philosophers are so deep in thought that they cannot handle taking 2 forks at the same time. So they can only take 1 fork after the other. So let's check our necessary conditions for deadlocks. We have mutual exclusion. We need both forks in order to eat, otherwise we can't continue eating. And if we can't continue eating, or if we can't start eating, then we're going to starve. There's hold and wait. So if I take my left fork first, for example, then I keep this left fork and until I get the right fork. So none of the philosophers has the idea of taking both forks at the same time or putting back 1 fork if the other one is currently in use. And of course, you can only use the left and right one that are next to your plate. So you cannot just reach over the table to another fork. That would be an interesting variation of this problem, but not a valid here. And it's not there is no preemption. So of course, it's not appropriate to just grab the fork of another philosopher while that other philosopher is eating. I mean, that would cause a big mess. So does this necessarily lead to a deadlock? Now, I'm not going into too many details here. These are lecture videos, but you should really take a look at the different solutions. So we found an incorrect solution. We found a correct solution, which is horribly inefficient. And we also presented an efficient, correct solution. So I would recommend checking them out. Even though this is a very artificial problem, you'll probably see it in all of the operating systems textbooks. So it's still a nice example. And of course, finding deadlocks in the real world is one of the other tasks of the current theoretical exercise. So this is not really a real world example, and this is obviously one we've discussed now. So the question is, how can we prevent deadlocks from happening? So we've seen our 4 conditions here, so the 3 necessary conditions and the 4th condition that has to occur. So we can do one thing or do one of 2 things. So we can either make one of the necessary conditions invalid. So these are so-called indirect methods to invalidate one of the conditions 1, 2, 3. So either you can use non-blocking approaches for resource allocation. That would invalidate condition number 1. Or you can only use atomic resource allocation. So you have to allocate all resources at once and cannot allocate additional resources. That would probably lead to a waste of resources because you might need some resources only for a short time when running your program. But still, this would invalidate necessary condition 2. Or to invalidate necessary condition 3, you would be able to enable the preemption of resources, for example, using virtualization with virtual memory, virtual devices, or virtual processors. So you could actually just generate new resources on the fly if it's a resource of a certain type from which you have multiples. On the other hand, there are direct methods, and these invalidate the circular weighting condition. So you could do this by introducing a linear or total order of resource classes. So essentially, all resources get a number, a unique number, and you have to allocate resources in that given order. So first 1, then 2, then 3, then 4. But there's no way to allocate resource 4 before you allocate resource 1. This would help. There's a formal way to describe it, which is shown here. So a resource R index I can only be successfully allocated before another resource R index J if I is less than J, or is ordered linear before J. Now this helps, but of course this is not very practical, because in the real world, well, which resource ordering should you actually choose? Which one would be actually appropriate here? And it would make life very hard for a program. You could also then imply rules to prevent deadlocks using methods at design or implementation time. And we've also discussed safe and unsafe states to prevent and analyze deadlocks. So these are also a bit more complex. So I'm not going to summarize them here. Please check them out, they're important. So deadlock detection and resolution, how can we work with this? So the very common implementation is shown in the picture on the right-hand side. So we're just doing nothing. So deadlocks are just silently accepted because they are rare. They're usually a programmer error. And we're calling this the ostrich algorithm because ostriches are supposed to just put their head in the sand. I think that's actually a folk tale and they're not doing it, but of course it works quite well. So we're just ignoring the problem by looking away. And if a deadlock occurs, well, you can kill processes by hand if you recognize it, or in the worst case, you just reboot your machine, right? I mean, what can happen? An alternative, as we've seen, is to create a resource graph and search for cycles. So this has a complexity of O of n. So this means it increases linearly with the number of nodes in our graph. So for a million for a million resources, that doesn't look too bad, but still it takes a lot of time in the real world. You can do this, but you can probably not do this at every resource allocation, but maybe you can do this every now and then. So you'd have to have a trade-off between high overhead and maybe some waste of resources, which you cannot allocate first. And finally, if you detect a deadlock, you can try a resolution. And well, you can terminate processes to release resources. You could preempt resources if you would be allowed to do this, and then start with what we call the most effective victim. So whichever process is least affected by preempting it. Or you could try to do some trade-off by implementing a balance between damage and effort. But to be honest, I have never seen stuff like this implemented in the real world. So yes, this is operating systems theory. This is still important because deadlocks are real world problems, but all these resolution approaches, even with the powerful hardware we have available nowadays, have relatively little practical relevance in the context of real world operating systems. So still, you should not forget them because they still make very nice questions for exams and exercises, but we're concentrating on problems that show up in code in the real world. And then we have seen the compilation process. There's an S hidden behind the graphics on the right-hand side. So we've seen all the steps in a typical compilation process for a C program. So we start with, what we call GCC is actually just front end, which calls the separate parts of the compiler in turn. So it starts handing over C code to the preprocessor. So this expands includes to have header files. This handles macro definitions. And the preprocessor then spits out another text representation where no more preprocessor macros are included. This is then handed to the compiler itself, and the compiler itself does a syntax and semantics analysis to then generate simpler source code from the C source code. So then we have transformed this into a machine language, which ultimately can be understood by the machine. Still, it's a textual representation, this assembler representation. So the assembler is a tool that generates object code from the source code, which is in assembler. So we've overloaded the word assembler here for the language and for the tool, unfortunately. And this generates what we call object code. So these are already machine instructions, binary instructions that could be executed by the machine, but they're not complete. So if your program consists of multiple parts, so if you link libraries, or if you have separate source files, C compiles each source file separately. So you get a number of object files and possibly of libraries that you want to link. And this linker then resolves all these open things, like I have a function that's actually defined in another C source code file. So whenever I call this function, I need to generate a jump or a call instruction to the address of that function, which is in the other file. So the linker's task is actually to go through all of the object files to look for any unresolved symbols and then to patch them up and to figure out if everything's complete. And then, of course, add the libraries. Now, after the linker has run, we have an executable file, so a file on your disk, and then you can start it by typing its name in the command line or double-clicking it or whatever. And then another part of the operating system comes into play, which is the loader, and the loader is responsible for taking this executable file, loading it into main memory, and then it's started by the operating system. Now, very often, this step from compiler via assembler is omitted. So very often modern compilers generate object code that can be linked directly without generating an assembly intermediate representation. Nevertheless, you can always request this intermediate assembler output if you want to take a look at how a certain C function is represented in the assembler of the machine you're compiling for, usually by passing -S as an option to the compiler, and then it generates assembler source code instead of an object file. All right, so this binary file, this executable that's generated, is in a specific format, and for Linux, for example, and very many other Unixes except for macOS 10, it's the ELF format. So macOS 10 uses its own format for historical reasons, which is called Mac-O. So Mac is the kernel of macOS 10. And Windows uses yet another format, which is related to a previous Unix format, which was called COFF, the Common Object File format. And Windows uses X or ECOF, whatever they call it nowadays. But all these are pretty similar. They're just different details. So we take a look at ELF here. So ELF files are not just the executable files that are loaded into memory and started, but they have a certain structure. So they have a header identifying them, shown here on the right-hand side. So there's a magic number. A magic number means it's just a specific string of bytes, which is hexadecimal 7F, and then the 3 ASCII characters, capital E, L, and F. So this always identifies an ELF file. So the operating system, when you start a program, checks if actually this signature, this magic header, is at the start of our ELF file. And if not, it usually refuses to execute it. And then this ELF header also contains information about which architecture, which operating system this was compiled for, and a number of other details. So the important stuff then is the program header table, which just contains links to the other parts. And we've seen parts of our program, the text section or text segment. We had the question last time if section or segment would be something different. In this case, they're used interchangeably. So text contains executable code. So machine instructions. Read-only data contains data which are constants. Data contains global variables which can be changed. There's also BSS for uninitialized global variables which are initialized to 0, and so on. So we've seen that you can look at ELF files using a tool called readelf. And if you do this to a linked program, you see you have a number of different things. So readelf can, for example, print a symbol table of a file. It can print the tables of an ELF file, and so on. So the linker actually then takes all the object files, which are usually indicated by .o at the end, and binds them together in this executable, and it adds some important stuff like the CRT0 startup code. So your program doesn't start at main, as we mentioned already last time. CRT0 cares about initialization of variables here. For example, initializing, variables in BSS to 0, calling C++ constructors, and then it jumps to main, and it also handles return values like the return value from main and passes it back to the kernel. The linker also adds libraries like libc, and then it creates a final executable if there's no errors to be found. Now, in object files, addresses of variables and functions are not resolved. So whenever you access a variable or a function in a different source file, for example, which then ends up in a different object file, the linker's task is to actually link them together, so to patch the addresses there. And all of these symbols are usually contained in a separate ELF section. So for example, debuggers can use them and show you so you can access variable names instead of memory addresses, which is much more convenient. And you can display this symbol section using, for example, readelf to take a look at the addresses of variables and functions. Then we had a quick introduction to virtual memory and process memory layout. So we've seen, and we'll go into more details here, that most Unixes require memory management units. So Linux also does this, except for some special versions called UC-Linux, which does things quite a bit differently for small microcontrollers. But let's ignore this for now. So the MMU actually translates the addresses generated by your program, which we call virtual addresses, into addresses that are actually delivered to your RAM in your machine, so physical addresses. And this is done using a so-called page table. So page table is what's shown on the right-hand side here. So it's essentially a tree of page table entries. So what you do is you split this virtual address into separate pieces, and these separate pieces then first the most significant bits index top level, then the next significant bits index the second level, which is pointed to from the top level, and finally you end up at the page table entry, which then gives you the physical address which you want to use, and also some additional information about that physical address, like is this physical address readable, writable, executable. Now you can't do this for every address separately, so that's why you split your address space in so-called pages, for example, 4 kilobyte pages. Otherwise, this page table would be much bigger than all the data you need. And for 4 kilobyte pages, if you have a sparse page table, which is the common case, then you can actually make this manageable. So you protect and you map using the MMU. And the problem is that the page table is also in main memory. So that would mean for every address you generate, you would need like 3 accesses to the page table to main memory to actually resolve the physical address. Now, this is very expensive. If for every memory access from your program, you would need 3 additional memory accesses. So that's why you usually cache most recently used page table entries in a hardware structure, which is part of the MMU. And this is called the TLB, so the translation look-aside buffer. So what virtual memory achieves is shown on the left-hand side here. So each process has the illusion of having the whole virtual address space of the machine, for example, 4 gigabytes on a 32-bit machine for itself. Now, these 4 gigabytes aren't completely true because there's usually address space reserved for the kernel, but let's ignore this now. And of course, this makes it easier for the linker because every program can now start, for example, at address 0. In Linux, for historical reason, it actually does not start at address 0, but there's actually no reason it could not. So you can link all processes at the same virtual addresses. So of course, if we run several of these processes at the same time, our memory management unit then takes care that these accesses, for example, to address 0, go to different physical addresses, because otherwise we would overwrite data or use code from other processes here. So that's the trick that happens. And managing the MMU is one of the more complex parts when you write an operating system kernel, and one of the very much error-prone parts, because you have to get everything right. Otherwise, you can create a number of security problems here. Then we took a look at what happens when we use fork. So we've seen fork uses copy on write. So if we use fork, then essentially we get a copy of the page table for the new process, and we are changing all the access permissions in the page table entries to read only, or read or execute for code pages. So we take away the write permissions, and this means we don't have to copy the whole address space, which can be large, but we only copy the page table, which is much smaller, and modify it accordingly, both in the parent and the child process. And whenever a parent or a child process now tries to write to one of the data pages, which now have no longer a write permission after fork, then an exception is generated, the operating system is called, and then the operating system does a copy, but not of the whole program space, but just of that one 4 kilobyte page, which is affected. So this makes the whole thing much faster and saves a lot of memory, because the other thing that usually happens after fork, as we've seen, is exec. And exec just throws away all these nicely copied page tables and some entries here. So if we had copied the whole address space, we would just throw it away immediately after the fork. If we do an exec in the child process, that doesn't make too much sense. So here, well, exec just takes the ELF file that we specify as the parameter to exec, loads it into memory, replacing the complete address space, which was originally a copy before. And since we have copy and write, we modify everything. We get our own copy of everything. And this is filled by the operating system, by the loader, with whatever is part of your new program that you're executing. So this was a quick overview of what we discussed in last week's lectures. So we have a theoretical exercise, obviously, and this is about deadlocks and the software development process. And we're handling two things here. So as I already mentioned, deadlocks are an important problem. Deadlocks are a problem that can happen if you do like parallel processes, parallel threads. It's hard to reproduce because race conditions do not always occur when you run a program, but usually they occur only after you send the program to a customer and the customer is goes crazy because of that. So, and they're much more difficult to debug because, you really have to figure out where this deadlock occurs, and then you have to find the situation when it occurs. This is not easy. On the other hand, we're talking about the software development process, and that's important for me and probably also for you, because this is very often nowadays hidden behind complex user interfaces like Eclipse or something, and stuff happens magically. So you push a button and your source code compiles and it links and you get an executable. I actually want you to understand a bit of what goes on there. So if you have a bit of an insight, then you can also try to gain back control over what you actually compile and execute. So you get a bit more background knowledge of what actually goes on here. So this was our review, and well, Q&A. Well, I wasn't sent any questions unless I managed to ignore an email. That would be a shame. So are there any questions on this? There are. If you write multi-threaded code in something like Python, will the interpreter libraries handle these problems for you? No, usually not. So Python also provides, I guess I'm not an expert in Python, but I guess multi-threaded code in Python also provides semaphores, also provides probably like in Java monitors, as we've seen in the lecture, which would be an alternative. So usually you can still create deadlocks. So sometimes you have something like synchronized methods in Java, which are already automatically providing mutual exclusion, because a synchronized keyword in Java means that this method has exclusive access to, but this still doesn't provide deadlock problems because a static analysis to do deadlocks. So essentially just looking at your program code to figure out if there are deadlocks. This is a hard problem for general code. We have some examples in the exercises for you to look at, but doing it in a statical analysis way to ensure that there are no deadlocks is, with current tooling, impossible. Next question here is multi-threading really common? Is this something most programmers know about and use, or are there likely programs in production with potential deadlocks? Multi-threading is common. So every program that's more complex and has to do things in the background is using multi-threading, obviously. So like your web browser, for example, when you click on something, it loads images in the background using separate threads when it has already loaded the main web page to speed up your loading of pages, for example. Is this something most programmers know about? Well, they should, at least when they took an operating system lecture, obviously. But there are programs in production with potential deadlocks. I'm pretty sure about this. I would need to look up examples, to be honest. But there are programs in production which, there is actually a nice example with some sort of a deadlock. This is about scheduling priorities. So you've probably heard about the Curiosity Mars rover, and this Mars rover was deployed on Mars, and it was running successfully for a couple of days, and then it stopped working. And the engineers at NASA found out that the reason it stopped working was that a low priority process was actually holding a resource that a high priority process was requiring. And this high priority process then didn't get access, so the whole system couldn't continue to run. And what the NASA engineers did back then was they actually uploaded a patch to the operating system over a radio link to Mars, which takes about, I think, a day or something to arrive. So it's not really an interactive use of a shell. So this robot was running, I think, QNX, which is a Unix-like operating system. And they actually did something that created an order of resource allocation. We'll take a look at this when we discuss real-time scheduling. So this order of allocation would be something similar as one of the prevention methods. So they actually changed the scheduling method of the operating system and then restarted the thing, and then it continued to work. So it happens in real life, and if it happens on Mars, it's not that easy to reset the machine. Well, until we obviously send Elon Musk up there, and then we could probably send him a message saying, go and push the button, right? Okay. Next question by Howard is, does the symbol table include only objects defined in the O file, or also objects used by the file that it expects to be defined in another O file? It also has, undeclared things. So it contains all the functions and global variables that your O file has, and it contains also all the unresolved references. So which functions are used in this object file, and then the linker has to look up these. If it finds them, that's okay. We can actually do maybe a bit of a live coding session here for a change. Live coding is always fun. So let's see if I can get this to work. Live coding without preparation is always something that can go wrong, but I hope that's okay. So let me share one of these many terminal windows I have here. I hope it's that one. Yes. So let's say we have a function foo.c, and there we have a function int foo. That doesn't take parameters. We don't need any. And with this function foo, we call a function bar. And maybe we also want to access a variable here, which we do with extern x. We call bar of x. So when we compile this to an object file, which we do with cc-c, then I get an implicit declaration. Yes, my compiler complains because I need a prototype, right? So I add a prototype here. It complains about a non-void function that does not return a value. Yes, let's program it clearly. Let's give it a value. So now this is obviously a Mac. This is not obviously, but it's Mac. I'm using it. I'm running here. So I can still try to run an m on foo.o. And yes, here you see things. So here you see a capital T symbol. So capital T and foo is the function we defined. So this means we have a function foo, which is defined in this file here. So you see the compiler automatically prepends all our symbols we use ourselves with an underline in order not to conflict with library symbols of the same name. So library symbols usually don't have an underline. And then we have, well, some temporary variables which are used by the compiler. Let's ignore them. Then we have two capital U's here. So first we have a capital U bar, which is our external function, which we're calling, which is obviously not defined here. And the second one is the variable x, which we pass to bar, which is also undefined. So when we try to link this, we see we get bar and x are undefined. Our linker complains, and also our linker tries to call main. So it tries to link crt0.o, so the C runtime startup, which tries to call main, and this also fails. So our linker would complain. And if we would now link a separate source file or object file that contains definitions of foo and of x and probably of main, then our linker would be happy. All right, short live coding demo. Let's go back to the slides when I can find them. Here we go. All right, so more questions. Lots of more questions. Would it also be possible to post all the theoretical exercises for the semester now? Sorry, no. There's a very valid reason for them. For that, they don't exist right now. We're doing them by the on demand, like by checking how far we can proceed, because we're not reusing all the ones from last year, obviously. So sorry, no, we can't provide them too much in advance, I'm afraid. So Manus gives an example of multi-threaded programs, mobile apps, because they'd otherwise hold the user interface thread and stop the phone from being responsive. Yes, that's a very good example. So if you do user interaction, usually the thing that should interact quickly is your user interface. So if you click the button, like to open a web page and you want to cancel it, and you can only cancel it when the HTTP transaction to fetch the page is terminated, then you would think your web browser would hang and you would not be happy. That would be one example. Is there a specific reason why the theoretical exercises have a deadline at noon and not midnight? Yes, there is. The specific reason is I probably didn't change it in the template, but I guess we can also put the deadline at midnight. And yeah, that should not be a problem at all. We could also put them at Mondays, 12 o'clock, which is just before the solution is handed in. But since the theoretical exercises are not mandatory, actually it doesn't really matter too much when they hand them in. But if you would hand all of them in like a week before the exam, then we would be a bit busy. Okay, and there's another hint, like in JavaScript with its event loop architecture, which provides non-preemptive concurrency and nothing to really log. I guess knowing a lot about logs isn't really a requirement. If you don't have to log something, then you don't need to know about logs, obviously. I'd have to check. I have programmed JavaScript, but not in that detail. But if you can provide some nice examples where logging is relevant or where logging can be ignored, well, send them to me. They might be interesting to your fellow students. All right. So another question here from Stack Overflow. Yes, Stack Overflow is so useful, right? JavaScript has no locking semantics because Java thread is not a multi-threaded language. That solves the problem very easily. Yes, if you don't have multi-threads, you don't have parallel activities, and then, well, obviously, yeah, you can get away with this. Nevertheless, responses on Stack Overflow with a grain of salt. So not everything there is correct. So usually, obviously, the highly voted ones seem to be correct. But still, it's like Wikipedia. There's no quality control except for like some peer review going on. Still, Stack Overflow is very useful and maybe much more useful than Wikipedia in this regard. All right, thanks for your contributions and your questions. So let's discuss solutions of the theoretical exercises. So I'll stop this recording now